water is hot. I think people around here think I'm compulsive or obsessive or something because I'm always washing my hands. But you know what? There's a flu going around, and I don't know what else on because of the bunkers. And who knows who's used my keyboard? There could be bacteria everywhere. Who knows? Maybe even superbugs. I'm Seth Shostak, and I'm grabbing more soap.
I'm Molly Bentley. Welcome to Big Picture Science, produced at the SETI Institute, where researchers investigate the nature and origin of life. On Big Picture Science, we step back to get the wide-angle view on science and technology. Antibiotics are a life-saving tool in the battle against bad bacteria, but they are losing effectiveness due to overuse and misuse. One culprit is the routine feeding of antibiotics to livestock, for example, on chicken farms. In this episode, the amazing story of how our wonder drugs became bird food, how some industrial farms are reversing the trend, and off the farm, an old therapy using viruses is being resurrected to help us avoid a post-antibiotic age. It's bacteria to the future.
If you've ever had a bacterial ear infection, you may have taken amoxicillin to clear it up. Amoxicillin also cures urinary tract infections. Bacterial pneumonia is often treated with levofloxacin. And Lyme disease, if caught early, may be stopped by doxycycline. Well, thankfully, we still live in the era of antibiotics.
We've come to rely on their life-saving properties. We even take them for granted. But some people have lived long enough to remember the pre-antibiotic era, when a scratch could be fatal. Investigative reporter Maren McKenna discovered a story from that era in her family's history.
My great-uncle, my grandfather's younger brother, was a fireman in New York City, and in 1938, on his day off, he was polishing the brass in the firehouse in Manhattan, and one of those big, heavy nozzles from the fire hoses fell off a shelf and sort of scratched and bruised him. Didn't break anything, didn't cause a major gash. And a couple of days later, he started to feel feverish. And at the time, the only thing they had to control fevers was aspirin and kind of cold compresses and ice baths. There was nothing to actually kill disease bacteria. 5 weeks later, he died of organ failure, septicemia, what they then called blood poisoning, a really terrible death. And the only thing they had to treat him, that this is in his obituary, is that the men from his firehouse lined up to volunteer to give blood transfusions because they thought if they replaced enough of his blood, they could dilute the infection that was surging through his body. And that story is so poignant to me because he was infected 3 years before the first human trial of penicillin. And in just a few years later, he would have been saved.
Penicillin became publicly available in the early 1940s. What's striking about Maren McKenna's story about her great-uncle is that it was not an uncommon one prior to the introduction of penicillin.
Before antibiotics, infections from routine scratches could lead to limb amputation. An untreated strep throat might develop into heart failure. If we lose the power of antibiotics, deadly infections will be waiting for us. Our overuse and misuse of antibiotics has produced an international epidemic of drug-resistant infections, which some fear have already begun to usher in a post-antibiotic era.
We're familiar with the role that medical prescriptions play in this epidemic. Now scientists are paying closer attention to the role of routine antibiotic use on farms. What if I told you that almost 80% of all antibiotics in the U.S. are not taken by humans? They're downed by cows, pigs, and chickens, according to the FDA, and most of the drugs used in animal agriculture and human medicine are identical, contributing to the rise of antibiotic-resistant infections. In short, some farms have turned into superbug factories.
How did we get to this point where life-saving drugs have become animal feed? Maren McKenna is the author of Big Chicken, the incredible story of how antibiotics created modern agriculture and changed the way the world eats. She says that we need to go back to World War II, when our newfound ability to defeat deadly pathogens at home coincided with vanquishing our military enemies overseas.
After penicillin debuted, the pharmaceuticals that followed, chloramphenicol, streptomycin, and the tetracyclines, were not easy to pronounce, but were lifesavers for the body. Their debut came at a time when the post-war world was confronted with a need to rebuild the food supply. It occurred in the laboratory of biochemist Thomas Jukes, an emigre from the United Kingdom who worked in one of the first U.S. labs to manufacture antibiotics, Letterly Laboratories. But Thomas Jukes was not part of the company's antibiotic effort. He had been hired to work on nutrition.
The food system feels very fragile because of damage from the war, from cropland being ruined and flocks and herds being killed and fishing fleets being decimated because navies took them as spare vessels. And there are crop failures all over the world and what's called a meat famine here in the United States. And so there's great pressure to reduce the costs of food production, to feed the world as cheaply as possible, to protect this whole system, to keep it from crashing. And one of the things that livestock producers start doing is giving their animals cheaper feed and then looking for inexpensive supplements to up the nutrition of the feed. And that is Jukes' assignment. He is an expert in the dietary needs of chickens. And he's sent to do an experiment to find an inexpensive supplement to increase the nutrition of chicken feed. And so he sets up an experiment in which he tries things like synthesized vitamins and brewer's yeast and cod liver oil added to chicken feed. And he tries, based on some stuff he's heard from some scientists in the Midwest, he takes the dried, ground-up remains of a drug that his company has just begun making, which is aureomycin, the first tetracycline antibiotic, and he gives that to one of the groups of chicks in his experiment. And when he weighs all the chicks on Christmas Day 1948, the chicks that have gotten the dried, ground-up antibiotic leftovers have gained more than twice as much weight as any other bird in the experiment. And thus is the whole industry born. He realizes pretty quickly that what's going on is that there were tiny, tiny doses of antibiotic left in that manufacturing waste, which is kind of like the grains that are left over from brewing beer. It's a very similar process. And within 5 years, American farmers go from giving 0 antibiotics to their animals, because no one had ever thought of this, to 500,000 pounds a year. And now, of course, in the United States, it's more than 30 million pounds a year.
So the appeal of antibiotics initially was that it was fattening up these chickens. It's not that the drugs were protecting them from bacterial disease. And do we know why antibiotics fatten up chickens?
So the antibiotics create an effect in which they change the population of bacteria in the gut, the mix of all the different bacteria, in such a way that it seems animals take up more nutrition from the feed that they're getting. So they put on that tasty muscle that we like to eat faster. And it wasn't actually very long before someone thought, well, if this much antibiotic is having this fattening effect, would a little more antibiotic have a consistent protective effect? Probably in one of the early trials, someone noticed that the birds or other animals, maybe it was pigs at this point, that were getting the antibiotics not only were getting fatter, but also had a lesser rate of disease than other experimental animals. And so by the early 1950s, the Food and Drug Administration licenses tiny doses of antibiotics, different doses, for growth promotion, as it comes to be called, and also for preventive or prophylactic use. And those proceed for decades as a routine part of farming.
And that's the path to addiction, isn't it? If 2 pills make me feel good, maybe 4 pills will make me feel fantastic. And you can apply that formula to all sorts of things that we do in excess.
It's really interesting to me, looking back in the scientific literature, of which I read, hundreds and hundreds of papers from the 50s and 60s, that no one really seems to have thought this through. That is, they did interrogate what was going on in the animals themselves when the animals were getting antibiotics, but they assumed that if drug-resistant bacteria arose in the animals, then these effects that they were looking for of growth promotion and disease prevention would just cease to work, that the antibiotics wouldn't have any power anymore. They never seem to have taken the extra step of thinking, what happens when the bacteria leave the animal? If we make livestock into factories for producing antibiotic-resistant bacteria, where are those bacteria going to go? And it wasn't until the first foodborne illness outbreaks that were antibiotic resistant, a thing that had never before existed in the world. It wasn't until those started to occur that someone really put all the pieces together.
Can you compare the chickens from the pre-antibiotic era to those that are taking the drugs today? Would you be able to go into a farm and identify a chicken that had not had antibiotics and one that had, or could you tell from photographs from, say, the 20s or something?
There are a few places where we could do that today, because there are a few agricultural schools that have kept populations that they bred sort of straight. I don't want to say purebred because that sounds like a heritage bird, but that they have bred without alteration from birds that existed before the antibiotic era. So birds from the 1920s, birds from the 1950s, birds from the 1980s. And when they compare them, the difference is really striking. The older birds, the birds that came before routine antibiotic use, and also changes in the bird's genetics and changes in precision nutrition through the years, are much thinner. They're much more upright. Generally speaking, from before sort of industrialized poultry production began, chickens from then to now, we raise a chicken twice the size in half the time as we did back before all this started.
Now, we began giving antibiotics to chicken mainly to fatten them up, but the prophylactic use of antibiotics was also exploited early on, and you write about this, and I wonder if you could describe for us the brief fad in the 1950s, I'll see if I can pronounce this, to acronize meat. And I don't know if I can use the word acronize as a verb because it appears to be a fabricated word used in a slogan, but how does one acronize meat, and how did this become a fad?
I shouldn't be laughing, but I find the story just almost literally incredible. Except it really did happen. I have the evidence. I dug it up in old scientific papers and old newspaper advertisements and letters to the editor. Acronizing was the creation of the same company that came up with growth promotion to start with, Letterly Laboratories, who employed Thomas Jukes. And someone seems to have had the idea that if they had a fairly substantial market giving antibiotics to livestock as they were growing, maybe they could get just that more of a market if they gave effectively one more dose to the animals after they were dead. And so what acronizing did was it took slaughtered animals, chickens and pigs and fish. It was tried on cattle, but it wasn't as successful in beef. And after the meat was butchered and cut up, it was dropped into a solution of antibiotics. And it was approved by the FDA that when the meat was or fish was hoisted out of this solution, there would be left on it a certain portion of active antibiotic that still could kill bacteria. And the point of this was to slow down the growth of spoilage bacteria on the surface of a piece of meat so that it could sit in a grocer's or a butcher's cold case or in a refrigerated truck or a refrigerated railroad car for weeks instead of days without going bad.
Oh,
and again, this is
awful.
One of those, I know, this is the astonishing thing, is that the people who thought this up and had the best intentions. They wanted to reduce food waste. They wanted to get fresh meat inexpensively into territories where it could never have been gotten before. The center of Australia, the center of South America, the center of Alaska. You could truck raw chicken across the country instead of freezing it, and freezing wasn't as precise back then as it was now, and it tended to ruin meat more than it did make it tasty. And this happened for almost a decade, fully legally, with the approval of the FDA. More than half the slaughterhouses in the United States had licenses to acronize, which was specifically a term that was thought up by this company, Letterly Laboratories, part of American Cyanamid. So most of the meat and fish in the United States for about 10 years came with antibiotics, still living, still working on its surface.
But then what happened is that the chicken dipping workers started getting skin infections. And that was because they were handling this meat that had been acronized, a made-up word. Can you describe what started happening?
I've spent a lot of my career writing stories of disease detection, of when something starts to go wrong and how it's sussed out and tracked down. And so often there's just one alert doctor or nurse who notices that something has gone wrong and has to make the case to everyone else who isn't really listening. And that's what happened in this case. A physician named Dr. Reimert Ravenholt, who in the 1950s was one of the first disease detectives trained by the CDC and then went to Seattle and worked for the health department there, got phone calls from doctors all around Seattle saying that they were seeing blue-collar working men who had terrible skin infections up and down their arms and hands. They were like the infections caused by staph bacteria, but they were particularly bad and they were not responding to treatment, and that was the clue. When Ravenholt analyzed them, he discovered that they were antibiotic resistant, and he couldn't see any reason why these men were all affected, even though they went to different doctors, lived in different parts of town, until he discovered that they all worked at the same slaughterhouse. And this slaughterhouse had installed this process, acronizing, had paid the licensing fee, had been trained by the drug company, and they were very, very proud of what they were doing because, of course, they thought they were making food more safe. And so when Ravenholt dug into it further, he discovered that the chickens that were being sent to this slaughterhouse from farms around Seattle had already been dosed as they were living with antibiotics by the different farmers. So effectively, the bacteria in the chickens were getting an extra dose of exposure when the meat went into this solution. And that sort of revved things up. Ravenholt, who's still alive, described it to me as like throwing kerosene on a fire. And that made sure that the bacteria were superbugs, and it was those superbugs that were making the men ill.
In a moment, we'll hear more from journalist Maren McKenna on how superbugs created on the farm make their way to your dinner plate, and how the poultry industry has begun weaning chickens off antibiotics.
Then later in the show, can viruses help us avoid a post-antibiotic wasteland? It's Bacteria to the Future on Big Picture Science.
The plump fryers you see on the rotisserie today have replaced the scrawny birds of the pre-World War II era, in part thanks to the routine use of antibiotics. Many of the drugs mixed in with their bird food are intended to make them fatter, and by the way, are also given to other livestock such as pigs and cows. But these are the same drugs we use in medicine. Consequently, the prevalence of antibiotics on industrial farms has contributed to the rise of superbug infections in us.
We'll hear how the bugs travel from the farm to your dinner plate. But first, how did they become such Teflon titans, impervious to our most powerful drugs in the first place? Well, the bacteria are just taking advantage of the same process that over deep time created the prefrontal cortex in humans and echolocation in bats. Antibiotic resistance is a product of evolution.
The transformation takes place through genetic mutation. As it is the dictate of natural selection that the fittest survive, those bacteria that have a mutation that resists our drugs live to pass their antibiotic-resistant DNA to the next generation of bugs. Over time, these bugs become superbugs. This is truly a case where what doesn't kill you makes you stronger.
So the antibiotics are taken in by the animals as part of their feed, and they descend, as the feed does, into their guts. And there they have an effect on the bacteria that live in the guts of chickens and cattle and pigs and the guts of every living thing, which is what we've come to know as our gut microbiome or our gut flora. That's this community of many varied types of bacteria that help us extract nutrition from our food and help us synthesize vitamins, and that we really could not live without. So some of those bacteria are bacteria that, if they escaped the animal, we would consider pathogenic bacteria, bacteria that can cause disease. And some of those bacteria, because of the influence of the antibiotics entering the guts, either become resistant to the antibiotic or already possess some mutations that would tend them toward resistance, and their number are increased by the presence of the antibiotics. And when I say resistance, what that really means is just that bacteria have learned to protect themselves against the action of the antibiotic that is meant to kill them. They've learned to toughen their walls or to turn the antibiotics away physically so that the antibiotics don't kill them. So now those resistant bacteria, like the antibiotics, are in the guts of the animals. And as happens with guts, the gut contents are going to leave. And that happens in two ways. While the animals are still alive, resistant bacteria pass out of them with their manure. And that means that that manure can get into the farm environment and pass from there into the rest of the environment by stormwater, groundwater, dust on the wind, on the feet of rodents and insects, even on the skin and the clothing of farm workers. Those bacteria can pass onward in a way that's very difficult to track. Or more practically speaking, when those animals are slaughtered and become the meat that we eat, those gut contents can splash onto the meat and travel with it into restaurant and home kitchens, and then onto our plates and into our bodies in turn.
And the bacteria keep living while they're on this journey to our plates and to our restaurants?
Sure. And it's actually a really fascinating process because take, for instance, those bacteria that passed into the environment. So they could go on and pass that resistance down to descendant bacteria when they reproduce. But what also happens is that when bacteria die and just kind of like come apart, the DNA that conferred resistance, the mutations that protected them against the antibiotic, can then remain in the environment and be picked up by other bacteria. So certain bacteria can become kind of like, I think of it as like a hand of poker, where the bacteria are assembling the best possible cards to be as dangerous as possible, which from a bacterium's point of view is really just that they are as defended as possible against threats.
Okay, so these bacteria, they make their way into us. Are there any bacterial infections that we know can be traced back to the use of antibiotics in chickens?
Yes, absolutely. And in fact, over the years, as molecular tools for diagnosis and lab identification have gotten better, the ability to trace back to farms has gotten more and more precise down to the genomic level. But it's very clear now that there are outbreaks of resistant, for instance, E. coli, Salmonella, Campylobacter, Shigella. These are all bacteria that are naturally resident in animals' guts, become resistant, and then pass out of the animals in various ways. You know, it's very clear, due to work done, for instance, by the Centers for Disease Control, that specific bacteria in outbreaks can be tracked back to the use of specific drugs, and in many cases down to the use on specific farms or to meat from specific processing plants.
Let's talk about solutions. It's always helpful at this point because it can get distressing. And I wonder if you could tell us the choices made at the chicken processing company Perdue to stop using antibiotics and how that experiment has gone.
This is a really interesting story to me. Because, of course, at a certain point after antibiotic resistance from agriculture started to emerge, there was pressure from at least some governments to stop. So pressure from the regulatory side, first in England, then in Europe, and it took the United States a long, long time to get going on this. But there was always a question of whether the actual producers were going to respond to regulation. So into this open question in the United States walks Jim Perdue, the grandson of the founder of Perdue Farms and the son of Frank Perdue, whom people of a certain age will remember from his TV commercials about it takes a tough man to make a tender chicken. So Jim Perdue, in 2014, calls a press conference at the National Press Club building in Washington, D.C., and says to the assembled press, I have a message to deliver. We're not going to use any antibiotics in our chicken. In fact, we haven't done that for a number of years. And it turns out that they had begun being suspicious of the utility of antibiotics in about the early 2000s and had been running tests on their contract farms ever since. At the point at which he made this announcement in 2014, they were already substantially antibiotic-free, and now they're about 99% antibiotic-free. And this was a challenge to the rest of the poultry industry and the rest of American meat production, and he was at first not at all popular. But now most poultry companies, not all, but a significant proportion, have followed his lead. So what did they do? So first, they wanted to make sure that antibiotics weren't conferring a benefit that somehow they weren't perceiving. So they ran a test using pairs of barns in farms in different ecosystems up and down the East Coast. And they gave one barn, the birds got feed with antibiotics, and the other barn feed without antibiotics, but otherwise all the conditions were the same. And they discovered that though back in the 1950s, there might have been a 10 or 15% gain in growth from antibiotics. Now it was down around 1%. So they could take growth promotion off the table. They wouldn't need to use the antibiotics anymore. Then they had to tackle, are antibiotics doing other things to protect birds in these very large barns that we now raise them in with 25, 35,000 birds at a time? And so what they did, and this is fascinating to me, is that they really did turn back to older practices. For instance, it's now quite routine for livestock to eat the protein of other slaughtered livestock. There's an entire industry, the rendering industry, that takes bones and feathers and hooves and so forth and bakes and sterilizes it until it's just kind of ground, disassembled protein.
Well, that's
that
how
gets added.
mad cow disease became a problem.
That's right. Rendered protein is sterile, but it's also not necessarily a very high quality protein. So Purdue took rendered protein out of their animals' diets, out of their birds' diets. And they also took the discards of industrial bakeries. It's called bakery meal, but it's made out of leftover bagels and danishes and stale cookies and so forth. Again, a sort of recovery industry that turns that discarded food back into something useful. Having taken out the bad stuff, they then started adding in good stuff. So they started giving their birds feed that was laced with thyme and oregano and other herbs that have a kind of natural sterilizing. They gave the birds an opportunity to exercise. So Purdue put hay bales and scales and shipping pallets in the barn so the birds could hop up on things and run up them and jump off and flap their wings a bit. And finally, and this is a thing that I think is just so poignant, they decided to cut windows in the walls of all their barns, which previously had been solid-walled metal and dark with a certain amount of light, artificial light a day. And now the birds can get sunlight on their feathers. And that probably helps with some kind of endogenous vitamin production, but more than that, it allows them to have something more approaching a natural life. And all these things are good for the bird's health as well. And the thing that I find so charming is that because these are sort of older things that grandparents or great-grandparent farmers might have done, I suspect they are also making the birds tastier, because exercise and a varied diet and the ability to absorb sunlight, those are all things that farmyard birds used to do. And chefs, for instance, will tell you that a farmyard bird is tastier than an industrial scale bird.
Well, I've been thinking about this story from the perspective of the chicken. And we have learned a lot about the benefits of good bacteria for our own bodies, for digestion and overall health, and the danger that antibiotics present to killing off those friendly bacteria. But I wonder if chickens also have good bacteria. They must. And do we understand the consequence of killing off their beneficial microbiome by feeding them antibiotics? They must have no friendly bacteria left.
So it's interesting that you ask that. I think the first answer is that for a long time, people just accepted that this worked and didn't really investigate the downsides. But there are companies right now, very large chicken companies, that have decided to move away from antibiotics. And among the things they give the birds are pre- and probiotics. So things like the kind of bacteria that are in yogurt, for instance. And just as we take yogurt or take probiotics in order to enhance the diversity of our microbiomes, that same effect in meat chickens is causing them to stay healthy in an otherwise conventional chicken house in which antibiotics have been removed.
Okay, so the answer is yes, that even chickens have friendly bacteria in their gut, and they're made sick themselves. Not only do they make us sick, but those poor chickens are probably not in optimum health because they're living a life without the whole microbiome they need to be healthy.
That's right. We know that everything in the world has a microbiome, right? That the microbiome as a microbial world far outweighs and outnumbers us, what we think of as discrete human beings. So sure, chickens have a microbiome, and we were disrupting it deliberately in the way that we gave them antibiotics. And it's really interesting to me that very large-scale poultry production in some ways is going back to sort of old farmer knowledge by improving the diets of their birds as they take antibiotics out, adding in all these beneficial bacteria, and doing other things that stimulate the immune system in really a more natural way, in such a way that they find they can do without the antibiotics and not have their production or their bottom line harmed.
This does sound very encouraging, but what is your opinion as to how helpful this will be in helping us to avert a post-antibiotic world? Specifically, how far will these changes on factory farms go if they do catch on, and helping us avoid losing the efficacy of antibiotics?
The answer is it's complicated. First, there are countries that are much further along the road of going antibiotic-free than the United States are. The ones that have done the most are the Scandinavian countries and the Netherlands. And in some ways, the Netherlands is the furthest away. And in the Netherlands, for instance, which has tracking of antibiotic use and antibiotic resistance in people and in animals that's very fine-grained, you can see that when they really sharply reduced their antibiotic use, which began in about 2010, the rates of resistant bacteria in their animals start to go down. And following that by a couple of years, the rates of resistant bacteria in people as well. So that's encouraging. It shows us there's a real effect. The problem is Western Europe, which controlled antibiotics more than 10 years ago, and the United States, which just did, we are a rounding error compared to what's going on the very large farms that are rising in the developing world. Because as low and middle income countries, economies improve, their citizens are spending their new income on meat. It's one of the most reliable signals to an economist of an improving economy is that meat sales rise. So no country has an infinite amount of arable land. It's very reasonable for places like China and India and Brazil to turn to very industrial scale farming. And the question is, can they be persuaded to not make the mistake of supporting that farming with antibiotic use? If those countries can go that way, then maybe we can still turn the tide.
Maren McKenna, thank you so much for speaking to us.
Thank you for having me.
Maren McKenna is an investigative journalist who specializes in public health and food policy. She is the author of Big Chicken, the incredible story of how antibiotics created modern agriculture and changed the way the world eats. While taking antibiotics out of livestock feed is a promising development in the fight against the rise of antibiotic-resistant bacteria, it's not enough to stop the spread of these super-resilient bugs. But could help be on the way? Enter a very special virus.
In as little as 20 minutes, the cell can make several hundred copies of the virus, then the cell blows up, and those several hundred particles come out, and they're all ready to infect new cells, so they can very rapidly destroy a bacterial population.
It's Bacteria to the Future on Big Picture Science.
In listening to how industrial farming may contribute to producing meat laced with nasty antibiotic-resistant bugs, you might be thinking, I'll solve the problem by cooking the heck out of my dinner. That's Molly's approach, much to her husband's dismay.
This is my strategy when I cook meat for myself, for my friends, and my family. I bake it or I fry it until it reaches the temperature recommended by the FDA. How does that look so far?
I think that looks great. Looks like it's done to me.
It's not quite done yet. Oops. It's a little hot, sorry.
It's hot. In fact,
So you stick in a thermometer and you cook it until it's 165 degrees. Let's check this out. 164 is 5. All right, 165.
I would pull that right off because it's going to keep cooking.
And then I keep cooking it just a little bit longer.
Molly, it's going to get overcooked.
It's going to be fine. It'll be fine. We'll know that it's really cooked all the way through. Because my plan...
Take my piece off?
So my plan is that you just really cook it thoroughly, and then it prevents us from getting sick. Okay, I'm going to take this off. Do you have a plate?
There you go. That
Okay.
looks good.
And you know what? You're going to stay healthy.
Oh, yeah.
Ooh, let me turn on the fan.
Blackened chicken by Molly.
It's an interesting culinary technique and a reminder to bring my own bucket of chicken the next time I'm invited to dinner at Molly's. Okay, well, perhaps you adopted her way of sterilizing meat to combat superbugs. Cook it into a charcoal briquette. Well, that may be an effective measure at home to prevent infection, as well as inadvertently contributing to weight loss. But it's not enough, as journalist Maren McKenna tells us.
Most people don't run their kitchens like, Silicon Valley clean rooms, and most people don't cook their meat to the temperature of the surface of the sun. And those two things being true, there's always the possibility that some bacteria will survive either cooking or the conditions of a kitchen if they splash onto something else or onto a raw food or onto a surface. That's how foodborne illness happens every day.
The problem of antibiotic-resistant bacteria is bigger than what's growing in our kitchens. It's one of the great public health crises of our time. Here are some facts. According to the Centers for Disease Control, each year in the United States, at least 2 million people become infected with bacteria that are resistant to antibiotics. 23,000 people die each year as a result of these infections. A 2014 British study concluded that a failure to tackle drug-resistant bacteria will produce infections that kill an extra 10 million people a year worldwide by 2050. That's more than currently die from cancer.
While no study can predict the future with absolute certainty, any scenario in which antibiotics have lost their life-saving power is bleak. However, efforts are underway to prevent a post-antibiotic world. As we've heard, some industrial farms are phasing out the use of antibiotics in chicken feed. Also, scientists are looking for new sources of antibiotics, and we're all regularly reminded not to take antibiotics for colds or the flu or any viral infection, because this promotes resistance. Antibiotics kill bacteria, not viruses.
But hang on. There's a way in which viruses themselves might help kill bacteria. Bacteriophages, phages for short, are viruses that have an ability to destroy some of the most lethal strains of bacteria. Phages are the most ubiquitous bacteria fighters on the planet. Therapeutic use of phages to combat disease is an old technology that fell into disuse. It's being resurrected by scientists such as biochemist Jung at Texas A&M University. He has been studying phages for more than 4 decades and is head of the Center for Phage Technology at Texas A&M.
Approximately 2/3 of the cells in your body are bacterial cells, and they're just as much part of your body as your mammalian cells. So a community of bacteria always has phages with it, and you have communities of bacteria in your intestines, in your back of your nasopharyngeal cavity. Everywhere you've got bacteria, you have phages.
Kind of like fleas on a dog. Everywhere you have dogs?
Yeah, I guess, although some of us view the phages as the most advanced since they replicate so rapidly and mutate so quickly. They're very, very highly advanced. So it might be that the only reason we're here is to provide bacteria for them to prey on.
Let's get down to the lifestyle, if you will, of a phage. It sounds like if it's a virus, it's just a tiny bit of machinery. I mean, it's not even clear that it's alive, right? I mean, it depends on something else that's alive. But phage, if I remember my Greek correctly, means eat or something like that. Are bacteriophages viruses that actually eat bacteria?
No, the word phage was introduced by the father of phage biology, Félix Darel, a French-Canadian scientist at the Pasteur Institute, who's actually a volunteer scientist then, back in 1917. And he detected phages in fecal samples of dysentery patients and discovered that they could destroy the Shigella bacteria, and he came up with the word bacteriophage before they knew there were viruses or anything else, so it's just stuck.
I see. So they're not actually eating the bacteria. I suppose that would be like a mosquito eating an elephant. I mean, that would be kind of tough, right? But maybe you could describe what does happen. I mean, what would a phage attack look like from a bacterium's point of view?
Bacteriophage first has to absorb to the surface of the bacterium, and that's where the phage has to be able to recognize whether it's the right bacterium or not for its lifestyle. The most common forms are DNA phages, and so these phages inject their DNA into the bacterial cell, take over the bacterial metabolism very rapidly, and can, in as little as 20 minutes, the cell can make several hundred copies of the phage particle, and then the cell blows up in a process called lysis, and those several hundred particles come out, and they're all ready to infect new cells, so they can very rapidly destroy a bacterial population.
They cause the bacterium to blow up. You called this, I think, lysis?
Yes.
So what happens? Does it really blow up, or does a cell wall break? I mean, leaking out all these little phages that it's produced?
For the phages that most people consider the most dominant phages in the double-stranded DNA phages, the cell actually does explode, and that's because the phage, when it's ready to terminate its growth cycle, it will actually cause a pathway to occur that destroys the rigid cell wall that all bacteria have. And then once that's destroyed, then the cell blows up.
It sounds like a grim story for the bacterium.
Mm-hmm. And not only that, if you're the first bacterial cell in a population of 1 billion to be infected by a single virus particle, within a couple of hours, not only you, but all your friends are going to be dead and replaced by billions and billions of phage particles.
Now, your friends are not going to thank you for that.
No.
Well, how picky are these phages, Rye? I mean, does a particular phage, I assume they come in various varieties, a particular phage only attack a particular kind of bacterium? I mean, are they specific in their targets?
They're all different types of phages. Some phages are very specific and only look for a very particular species or even a subspecies of bacteria. Others are very generalist, and they will infect a very broad range of bacteria. Phages are so diverse, in almost any sentence that starts with the word phages is going to be an oversimplification.
Yeah.
And many people have a hard time understanding how there can be any bacteria out there if there's so many phages. And the answer to that is very simple. As long as the bacteria are present in relatively low numbers, they never contact with the bacteriophage. So you can have phage particles and bacterial particles sitting around in a solution, and they can sit indefinitely because they never come into contact. They're just such low concentrations. But once bacterial populations have a bloom, for example, and you get to very high levels, then suddenly they start making contact, and then the chain reaction takes place.
So from what you say, it sounds like it might be possible to either engineer a special kind of phage, or maybe you just select them out. I don't know how you would do that. That could attack antibiotic-resistant bacteria. I mean, you could co-opt these guys.
Sure, phages were actually used massively in the United States and all over the world as antibacterial treatments, even before there were any commercial antibiotics. So back in the early part of the 20th century, it was literally all over the world. It was done millions of doses, hundreds of thousands of patients were treated. So it was, in fact, for a while considered to be the magic bullet, the long-for magic bullet in the days before antibiotics were even dreamed of.
But why are you using past tense here? I mean, what went wrong with this approach? Sounds great.
The biggest problem, I think, actually was that it was premature. This was, in the 1920s, was 30 or 40 years before we even knew what DNA was. And so we didn't have electron microscopes. Everything was done basically blind. They didn't know the very basic biology of what phages were like. And so there was a lot of very inconsistent results for lots of different reasons. And the AMA commissioned a series of reports with varying degrees of negativity, but one most frequently cited was in 1934, where the major conclusion was that for the most part there had been no demonstrated benefit of treating with phages. So after that, the use of phages in Western medicine tended to die out. And that was about the time when the development of antibiotics over the next decade began to take over. And there was no more, at least for a long time then, for decades, there was no reason to even think about phages since we had antibiotics and we were never going to have problems with disease bacteria again.
My goodness. Well, it sounds like the tables have turned, and the phages
Yes.
might have another attempt on this stage.
Yes, I think I think it's true.
Well, let's suppose that we fall victim to a new strain of bacteria we haven't seen before. Maybe it arose in chickens, cows, or something else. And how do we marshal the phages to take that on?
That's one of the issues facing phage therapeutics. So the best example would be to describe what actually happened in the famous Tom Patterson case from 2 years ago. He was infected with a multiple drug-resistant bacterium when he was on a trip to the Mideast, and he ended up falling victim to a systemic infection. His blood had bacteria in it. He had cysts that were full of bacteria. It was and he was hovering on the verge of death in the intensive care for months. This bug was completely resistant to all the known useful antibiotics, and reached out to the phage community for phages that might be used on a compassionate use basis. So what happened was The bacterium that was isolated from his body was sent to various places, including our location and also to a U.S. Navy laboratory. And then we went about looking to see if any of the phages we already had worked on that bacterial cell. And then we went out and had to isolate new phages. We did a good old-fashioned phage hunt, we call it, no different from the way it was done 100 years ago by Durrell, just by looking for the ability to grow on a plate and to see if the phage could stop that growth. I think it took about three to 4 weeks between us and the Navy. There were sufficient different phages to try the treatment, and luckily it worked, and he certainly improved immediately after ejection of the phages and was able to leave the hospital within a month or a month and a half. So the answer to your question is, at least for most of the bacterial pathogens that we're dealing with, you actually have to test individual phages against that bacterium and look for one that works. And so in order to have any realistic chance of treating a particular infection, you probably have to have already pre-prepared stocks of hundreds of different phages in your refrigerator and go test them by some robotic way, hopefully, to see if any of them work against the strain.
So how do you see the role that phages will play in combating the threat of antibiotic resistance? Is it going to be the game changer we would like to hope?
I think at least for the next few years it'll be a last resort treatment, which it already is being used that way in the United States and also elsewhere in the West. The basic science is pretty straightforward, since if you find the right phages, which are abundant in the environment, so it's just a matter of relatively simple screening, you can find phages that for almost all disease-causing bacteria, we've been able to find phages quite easily. There are lots of issues, mainly having to do with the fact that no one's bothered to think about this for almost 100 years. There are a lot of issues to be worked out. I know the FDA is very concerned about this. They're interested in developing new strategies for regulating phage. There's intellectual property issues. There's regulatory issues. There's been very little investment in phage as therapeutics. I mean, I doubt there's been even $100 million in the entire history of phage biology invested in terms of therapeutics. So we're quite a ways away from generalized use of phage for human therapeutics.
So I take it you would certainly endorse the continued development of antibiotics.
Oh, absolutely. We're only now getting the tools we need for antibiotic 2.0. I mean, the biggest problem in my mind isn't the development of new antibiotics, but to try to make them more specific, because our microbiota are very important to us, and I think we no longer can just look for antibiotics that'll just kill any bacterium that walks in the door, which used to be the dream of the physician, to not worry about what the disease was, just to push a pill and be sure that's going to work. But I think now we have to worry about the consequences of that treatment on your own bacterial cells in your microbiota, and knowing that you're going to have a devastating result. So I think antibiotic 2.0 is going to be how we learn to develop molecules, chemical molecules, or larger than that, biological molecules that can distinguish between their bacterial targets.
Ry Jung, thanks so very much for speaking with us.
Okay, I'm glad to do it. Anytime.
Ry Jung is a biochemist, and he is the head of the Center for Phage Technology at Texas A&M University. So what we're hearing in the show is that, well, for one, there was a therapy that came along before antibiotics were developed and was dropped, phage therapy, and we can hope that it will be resurrected and it will help get us out of this mess.
Yeah, sort of a retrovirus fix for the antibiotic problem. But the other thing here is that it's more back to the future in the sense that the old way of raising chickens might also address part of this problem. It's an unintended consequence problem. Everybody was trying to do something good, improve the food supply, and some bad things came up. But I have to say that personally, I'm kind of encouraged by the fact that if we get our act together, we might be able to meet the challenge of the superbugs.
Thanks to the trio who are not chicken about producing our show: Senior Producer Gary Niederhoff, Operations Manager Barbara Vance, and intern Anna Katrina Hunter.
Thanks also to financial support from Rena Shulsky David and Sammy David, and to the William K. Bowes Jr. Foundation. Big Picture Science is produced at the SETI Institute, a nonprofit scientific and education organization whose scientists study the origin and nature of life, including the possibility of life on Mars. And a big thanks also to our listeners.
Your ears have been attuned to an episode of Big Picture Science called Bacteria to the Future. If you want to hear more Big Picture Science episodes, well, you'll find them in our archive at bigpicturescience.org.
And if you're a podcast listener but prefer listening to over-the-air radio because radios are seldom fattened up on antibiotics, check out the listing on our website of radio stations that carry the program. And if your local station is not on that list, consider letting them know you like the show.
Hey man, these bacteria don't look good.
So, who you gonna call?
Hostbusters!
Ready?
Ready,
Set phages to stun.
'cause we've got a lysis to kill.